So hello everyone, welcome to the channel. So in this video I'm going to show you how to perform a spatial and temporal analysis of water chlorophyll concentration using MODIS data in Google Earth Engine. So we're going to focus on the Gulf of California as a case study. So now let me explain about this particular dataset here. So this is our MODIS dataset. So the dataset availability is from 2000 to 2022. The dataset provider is NASA. And this is a core script. Using this script, we're gonna access this particular data set. And in the band section here, we're gonna specifically focus on this four bands here: the chlorophyll-a, that is chlorophyll concentration, and NFLH, that is normalized fluorescence line height, and POC, that is particulate organic carbon, and last, that is SST, that is sea surface temperature. So resolution of this dataset is around 4616 meters. There is almost 5 kilometer by 5 kilometer resolution. So let me navigate to Earth Engine here. So in the Earth Engine, so we're gonna map the chlorophyll, phytoplanktons, and particulate organic carbon concentration, as well as to analyze the sea surface temperature using MODIS Ocean Terra data in Google Earth Engine. And we're gonna focus on the coastal regions of California. So first we're going to define our region of interest using our latitude and longitude. So to create a region of interest, it is we're going to navigate to this option here called draw a rectangle. So once you did that, we're going to draw a rectangle over this Gulf of California. And here now we have this variable called geometry. So it contains the latitude and longitude. You can just copy this latitude and longitude and paste it here in this section, in this variable coordinates. So once you pasted those coordinate here, so this variable is going to contain this latitude and longitude of this study area. Let me turn this off here. And next we're going to create a variable called study area equals to geometry.polygon coordinates. And to add this layer, so the coordinates here refers to this particular variable called coordinates containing latitude and longitude of our study area. So to add this layer, we define map.addLayer study area with default visualization parameter and output the layer as study area. And center as object, we define map.centerObject study area with a zoom level of 6. So next we're going to load our MODIS ocean data into Earth Engine. For that we define a variable called MODIS collection equals to image collection NASA ocean data MODIS Terra L3SMI. And we're going to specifically filter the date from between 2020 to 2022. So for that we define dot filter date 2020 January 1, 2022 December 31st. Now we're gonna select the specific band called chlorophyll-a. So in this particular data set we have this band called chlorophyll-a, that is chlorophyll-a concentration. So to access this particular data, we define variable called chlorophyll equals to MODIS collection dot mean dot select. So we're gonna select this particular band called chloro-a. So this particular band here, chloro-a, from this data set. And next we're gonna add this layer. So for that we define map.addLayer chlorophyll dot clip clip study area, and we define the color palettes for the chlorophyll concentration, with the lowest level of chlorophyll concentrations are indicated in blue and the highest level of chlorophylls are indicated in red, and output as a chlorophyll-a. So now we're going to visualize the result here. So let me click this option called chlorophyll-a. So here you can able to visualize in this study area, that is in Gulf of California. So the red indicates the highest level of chlorophyll concentration, and the blue here indicates the lowest level of chlorophyll concentration, and the intermediate level of chlorophyll concentrations are indicated in this set of color here in yellow color, which indicates the intermediate level of chlorophyll concentration. So let me explain about this chlorophyll. So this is the dataset we are using for this particular analysis. So the chlorophyll-a, so units in milligram per meter cube. So the range of concentration is from 0 to 99.99 milligram per meter cube. So the chlorophyll-a concentration measures the amount of chlorophyll present in water, which is an indicator of phytoplanktons, biomass, and overall productivity of the ocean. So the unit is in milligrams per meter cube. So let me get back to Earth Engine. So it basically computes the mean chlorophyll-a concentration over the specific study area in the filtered timeline. And next, we're going to map the phytoplankton concentration. So for that, we're using this particular band called normalized fluorescence line height. So this particular band is referred to as a normalized fluorescence line height. Let me show you that. So the second band refers to NFLH, that is normalized fluorescence line height. So this specific the band which refers to the phytoplankton concentration. So for example, so we're going to define a variable called phytoplankton equals to MODIS collection dot mean dot select NFLH, referring to the normalized fluorescence line height. And to add this layer, we define map.add layer phytoplanktons.lib study area. We are setting the color palette starting from the lowest level of concentrations are indicated in blue and the highest level of concentrations is indicated in red. So output the layer as phytoplanktons. So now let me show you the layer here. Navigate to this layer section. Let me turn this off and turn this on. So now here you can able to visualize the color schemes here. So the lowest level of phytoplankton concentration is indicated in blue and the highest levels are indicated in red. So here we have two different set of color schemes here. One is it's indicated in blue and green and yellow. So the highest level of concentration is indicated in here in yellow and green here, which is indicated in the coastal part of this area here in California. Let me show you that. Let me turn this layer off. So you can able to observe here the highest level of phytoplankton concentration is being observed in the coastal part of this California. So which is indicated in clearly in the reddish part of this area and also the greenish and yellowish areas, and the lowest level of phytoplankton is indicated in blue color. So let me explain about this particular dataset phytoplankton concentration. So the phytoplankton concentrations are referred using this particular band NFLH. So unit is in milliwatts centimeter square micrometer steradian. So and the range is indicated from minus 0.5 to 5.03 milliwatts centimeter square micrometer steradian. So range is from minus 0.5 to plus 5.03. So this parameter measures the normalized fluorescence line height, which is an indicator of phytoplankton's health and chlorophyll fluorescence. So now let me get back to our Earth engine. So this particular will computes the mean phytoplankton concentration over the filtered period. So next we're gonna map the particulate organic carbon. So for that we define a variable called POC equals to MODIS collection dot mean dot select POC. So the POC here refers to this particular band here, that is the particulate organic carbon, which is given in milligrams meter cube, the unit is. And here we define a visualization parameter for this particular layer. We define a variable visparams2. We define the opacity to be around 1, and the bands we are to distinguish this particular data into three in a different color gray shades. We define POC, POC and POC. So to view this particular data in different gray shades, we define this, and we set a minimum value to be around 187.1 and the max value around 1470. So you can check the max and minimum value from here. So you can able to see here the maximum minimum is around 4 and the maximum is around 12,953.4, and we set the gamma value to be around 1. Now to add this layer, we defined the map.add layer POC.clip study area visparams2 POC, and let me show you this particular data set here. We're gonna navigate to this layer section. Let me turn this off, this layer, and gonna turn this POC, that is particulate organic carbon. So it will be displayed in the different gray shades in this image here. You're gonna visualize it now. So now in the image you can able to visualize here in the different color shades the whiter areas in this you can able to see that, which indicates the highest level of this particulate organic carbon. So let me show you that here. First we're gonna navigate to this option called layers. We're gonna click this option called settings, and in that you can choose your in customs we're gonna select this stretch 90, and and we're going to click apply. Or in case you want to view this in different color shades, you can click this option here and choose your color scheme and add a different colors to it. So I've added 3 different colors here. So I'm going to click apply. So now we're going to visualize it in the color here. So from here you can able to observe that the highest level of organic that is particulate organic carbon, it is observed in red. So a few areas that you can able to see here that indicates in red, and the next moderate level of this particulate organic carbons are indicated in green, which is observed in the coastal part of this California, and the lowest level of particulate organic carbons are indicated in this areas in yellow color. You can able to observe it. And now I'll explain about this particular data set, this particulate organic carbon. So the POC refers to the particulate organic carbon. The units used to measure is milligrams per meter cube. So the range is from 4 to 12,953.4 milligram per meter cube. So the particulate organic carbon is the amount of organic carbon found in suspended particles in water. So it is important for understanding the carbon cycle and the marine productivity. So this particular code computes the mean particulate organic carbon over the filtered period. So now next we're going to perform the time series analysis using sea surface temperature band in our MODIS dataset. So let me close this, and let me turn this layer off. So now to perform a time series analysis for the SST, that is sea surface temperature band from MODIS dataset. So first we have to stack the raster layer of the sea surface temperature band. For specifically we're going to focus on the sea surface temperature in the month January from 2020 to 2022. So we have mentioned the time frame here. So we have mentioned the time frame here, that is from 2020 January 1 to 2020 December 2022 December 31st. So first we're going to define the variable called SST collection equals to MODIS collection dot select SST. So here the SST refers to, so let me show you that SST refers to the sea surface temperature with a minimum value of around -2 to a maximum value of 45 degrees Celsius. So the temperature varies from -2 degrees Celsius to a maximum temperature of 45 degrees Celsius. So once we select our SST band from our MODIS dataset here, so we're going to filter with a specific calendar range here. So we're going to specifically focus on the sea surface temperature only in this month in January, so in the Gulf of California. So for that we define this dot filter, filter dot calendar range, the start and end time. The start time we defined as 1. The 1 here represents the January, and the 1 here represents the end time. That is end time also we are going to reference 1 here. So the start time will be 1 and the end time will also be the 1. So 1 will represent January and the start and end time will be from January. And so specifically the sea surface temperature we're going to focus on January. So for that we define as a 1,1 here, and with the unit we defined as a month. So in case if you want to visualize the sea surface temperature from January to July, so for that in that case you have to define the start time to be 1 and the end time should be 7. So instead of 1 you have to give it 7 in case you're selecting as July. So you have to give the end time as 7 and the unit will be month. So now to view this particular image, we're going to define the print SST collections. So here you can able to visualize here. So image collection NASA, this is this particular one SST collection. So I'm going to click this arrow button here. So here you can able to visualize the features, the list of around 93 elements here. Let me click this arrow here. So you can able to visualize this different images that is available within the specific time frame. So we have specifically selected start and end time to be January. So you can able to visualize it here. So next we want to make a stack from this SST collection here. So for that we define this variable called SST stack equals to SST collection. So referring to this variable dot 2 bands. Now let me minimize it now here. So here the 2 bands specifically this particular specifically used to stack the images. So it is very useful to stack the images. And after that, to add this layer, we defined map.add layer sst stack.clip study area is set as the default visualization parameter, and output the layer name as sst stack. And to view the information about this particular dataset, SST stack, we define print SST stack. So basically what this particular set of code does is it filters the MODIS collection for sea surface temperature for the dataset, particularly for January, and this stacks the SST images into a single multi-band images. So it's going to stack all the SST images into a single multi-band image. So in the console section, you can able to see here the previously in one image collection we have around 93 elements here, and in the second in the stacked image here. So in the one so once we apply the stack here, we have only one image which contains around 93 bands here. You can able to see that. Let me click this arrow here. You can able to see. So it gives us a time here. These indicates the date, and it indicates the data type and the projection. You can able to see that. So previously we had a one image collection with 93 elements, and now after that we have performed the stack here, we have one image with 93 bands. So now we're going to visualize the layer here in the layer section. So we're going to click this layer and click this option called SST stack. So here you can able to visualize it. Let me navigate to the layer. I'm going to click this option called settings here. Let me paste this here. Let me click band one. So in this particular section here in the SST stack layer here, you can select any images in the January month here. You can able to see 2020 2 refers to January 2, 3, 4, 5. You can able to see the different dates here. So for example, let me select this particular date, and I'm going to click this custom option here and click stretch 90, and I'm going to click apply. So here you can able to visualize the result here. So from this image here, you can able to visualize the darker area which indicates the lower temperature areas, and the whiter areas which indicates the higher temperature areas. So in the California, you can able to observe in this part of the coast has a lower temperature, low sea surface temperature compared to in these areas here. So towards the southern part of these areas here, you can able to observe the very high temperature being observed here. So it is varies from around 14 degrees Celsius to 23 degrees Celsius. So in this section has a very high temperature, and this towards this part of this areas has a lower temperatures, which is indicated in the darker areas indicates the lower temperature, and the lighter areas indicates the higher temperature. So now we have created a sea surface temperature. Let me close this, and let me explain about this particular data set. So SST refers to sea surface temperature. The unit is in degrees Celsius. The range is from minus 2 degrees Celsius to 45 degrees Celsius. And the description. So the sea surface temperature is the temperature of the water surface, crucial for understanding the climate, weather pattern and marine ecosystem. So this particular data set, the lowest value starts from minus 2 degrees Celsius to a highest value of around 45 degrees Celsius. So units is in degrees Celsius. So suppose if you want to download this particular phytoplankton concentration or SST sea surface temperature, chlorophyll concentration and particulate organic carbon to your Google Drive. So for that, we're going to define export.image.to-drive image phytoplanktons.lib study area, and description we're going to give it as a phytoplankton MODIS, and resolution is around 5000 meters. So the resolution of this particular dataset is around 4616. So for that, we define this resolution as 5000, and the region is study area, and coordinate reference system is given as this particular one, EPSG, the max pixel value here. So this is the maximum number of pixel to be exported. It is given here, and the folder, it is phytoplanktons. Similarly, to export the chlorophyll concentration, we define this, and for SST, that is sea surface temperature, and for similarly the POC, that is particulate organic carbon. So now we can navigate to the task section here. You can able to see that there is an unsubmitted task called POC MODIS, phytoplankton, chlorophyll MODIS, and SST. So this is the particulate organic carbon, phytoplankton concentration, chlorophyll concentration, and sea surface temperature. You can just click this option called run to export this particular data set to a Google Drive. So the task you can give it as this POC, and scale is the 5000 meters, and the file is in GeoTIFF file format. You can just click this option called run to export this particular image to your Google Drive. So once you exported this, you can just download from your Google account. So that is from your Gmail, from your Google Drive, and you can just use this particular data set to perform any analysis in your GIS softwares. So let me cancel this. So next we're going to create a temporal collection function to aggregate an image over a period of time from 2020 to 2022. Now I'm going to show you how to create a temporal collection function to aggregate an image over time. So this particular dataset MODIS is a daily dataset. So maybe you want to get an output from this data with a monthly or weekly or even seasonal format. So now I want to show you how to create a temporal collection function to aggregate an image over time. So now I'm going to create a function to create a temporal collection. So this particular function, which includes a couple of arguments like collection, start date, and num period, interval, and time units. So here the collection, which refers to the image collection to be aggregated, and the start date for the aggregation as a string. For example, we're going to start with 2020 January 1, and the num period here. So the num period, it represents counts the number of output images we expected. Also the interval refers the temporal difference between the output images, that is the length of each temporal period. And next the time unit. So the time unit for the interval, which can be a day, month, or year. So this part of the function makes a sequence, make a list according to the number of output images that is expected. So for that we define this variable called sequence equals to list.sequence. 0 represents and here we define the start as a 0. So the list is started from 0 row to the number that is already set for this particular, that is the number. So for that we defined the earth engine dot number num periods, which refers to this particular one here, and we defined dot subtract 1. So as we are starting from 0, we need to subtract. So we need to subtract the num period number from 1. So next we need to define the start date. So for that we define this particular variable called origin equals to date start date. So the variable origin helping us to convert the start date from a string to the date format, because we need to import the start date with a string format. So for that we define this variable origin equals to date start date. So now we need to return this list with image collection format. So for that we define return image collection sequence dot map function. So now we defined a function in each row of the list. Through the map we make a function that each row is considered as I, and we want to estimate the start and the start date and the end date for each row separately. So for that we define this variable called start equals to origin dot advance and dot number, so the interval which refers to this particular one here, and dot multiply each row that is represented as I, and last here the time unit. So the time unit which is similar to this one here, which defines the day, month, or the year. Similarly, the end date we have to define a variable called end equals to origin dot advance dot number interval and dot multiply dot number I dot add 1. So this particular remains same as the time unit. So the start here refers the start date of the current period calculated by advancing the origin by an interval multiplying I, and similarly the end date of the current period calculated by advancing the origin interval multiplying I plus 1. So now we're going to retain the collection. So for that we define the return collection dot filter date start and end dot mean function. So here we define the mean in order to get a mean image from the image collection. So for that we define this particular function dot mean function. And next we need to set our system time start and system time end. So for that we define dot set system time start comma start dot the millisecond function. So we are applying the millisecond format here. Next we define dot set system time end end dot millisecond file format time format. So what it does is the collection dot start and end function filters the image collection to include only one image within the current temporal period. And next is the mean function to calculate a mean image within the period, and the set function and add a property to the resulting image storing the start and end time as a metadata. So this function is a powerful tool for temporal analysis in Google Earth Engine, so allowing the user to aggregate an image data over the specified time intervals easily. So next we're going to create a weekly temporal collection from this MODIS data. So I want to apply this function to the available images for 2 years and convert them into a weekly format. So to do that we define this variable called weekly collection equals to create a temporal collection. So MODIS collection refers to the image collection, and the create temporal collection is our function here. We defined it here in previously. So this is our function create temporal collection. So this particular MODIS collection is referring to this particular variable here. So this is the variable referring, that is MODIS collection. So this daily MODIS image collection which is called for 2 years from 2020 January 1 to 2022 December 31st. So I want to convert this daily to a weekly daily format to a weekly format. So the MODIS collection refers to the image collection, and the start date which refers to 2020 January 1, and this is the number of output that is expected. So we aim to get weekly images for 2 years. So 1 year we have around 52 weeks. So for 2 years we expect 2 years we have around 104 weeks. And the one here which refers to the interval. So the interval, that is a 1 week interval. So 1 week interval we have represented as 1 here, and the unit refers to as week. And to view this information about this weekly data, we define print weekly collection referring to this particular variable, and we can see the result here. This is image collection, 104 elements. You can see there is around 104 elements. So next to create a time series chart for chlorophyll concentration and the sea surface temperature and POC. To create a time series chart, we define print UI.chart image.series the weekly collection dot. So the weekly collection, we can get the weekly chlorophyll concentration, so using the specific variable. So dot select, we are selecting this particular band from this MODIS collection, chlorophyll-a. This is a band, and based on study area, and reducer dot mean to arrive a mean data. So with a spatial resolution of 5000, and the system start time from 2022. So that is from start time refers to 2020 January 1, and we're gonna visualize it. So this particular chlorophyll concentration. So this is the graph which represents the chlorophyll concentration here. We're gonna click this. So you can able to view that from 2020 to 2022. So here he starts from January, February, March to December. So you can able to see there is a high level of chlorophyll concentration is observed in this period in March, April, May and June. So you can able to visualize in this set of months we have a very high chlorophyll concentration be observed in this set of months here, starting from April, May, June and July. And similar set of observation be also been observed in this 2021 here, starting from February or starting from May, April, that is from March, April, May and June. So there is a downfall in the chlorophyll concentrations observed in this set of months here in August, September, October and November. So let me show you some information about the chlorophyll concentration. So the primary productivity, so high chlorophyll concentration indicates a region with a high primary productivity, as the chlorophyll is a proxy for phytoplankton biomass. The nutrient availability, so elevated chlorophyll-a level often correlates with the increased nutrient availability, suggesting an area for upwelling or the nutrient runoff. And the ecosystem health, the changes in the chlorophyll concentration can signal a shift in ecosystem health, potentially indicating the eutrophication or harmful algal blooms. So the applications, so the fisheries management, identifying the productive fishing zones by locating areas with a high chlorophyll-a concentration. Water quality monitoring, detecting and monitoring the algal bloom and assessing the potential impact on water quality. And the climate change studies, so understanding the impact of climate change on the ocean productivity and carbon cycling. So now let me close this. And similarly, so to create a time series graph for the SST, that is sea surface temperature, so we defined UI dot chart dot image series weekly collection dot select SST band and study area EE dot reducer mean and the spatial resolution of 5000, system start time, and this second graph which represents the sea surface temperature. I'm going to click this here. So you can able to observe here the temperature is varying from 18 degrees Celsius to 28 degrees Celsius. So the lowest sea temperature has been observed in this year from January and February, March, April and May, and after that there is a very high temperature being observed in this set of year starting from June to November. So there is a decrease in sea temperature during this month in December, February, March and April. You can able to see this. So the sea surface temperature, the climate indicator. So SST is a critical indicator of climate pattern and changes influencing weather and climate system. The ocean circulation, SST data helps in understanding the ocean currents and circulation pattern which affects the global climate. And next is the marine habitat. So SST influences the distribution and behavior of marine organisms including the fish migration and breeding patterns. So applications, the climate change monitoring, tracking the changes in SST to study the impact of global warming on oceans. Weather prediction, improving the weather and climate model for better prediction of phenomena such as El Nino and La Nino. The biodiversity conservation, managing and conserving the marine biodiversity by understanding the thermal habitat of the marine species. So let me close this. And similarly, to view the time series chart for the POC, that is particle organic carbon. So for that, this represents third graph which represents it. So let me click this. So you can able to visualize the particle organic carbon which is represented in the unit milligrams per meter cube. So starting from 0 to 200 milligrams per meter cube. So you can able to observe in this set of period has a very high concentration of particles organic carbon. So you can able to observe in this set of years, and there is a downfall in this year in this month here during October and November, and similar set of being observed in the 2022 years towards the 2022. So the particle organic carbon, so the carbon export, so POC represents the carbon contained within particulate matter which can be exported to deep ocean, playing a role in the biological carbon pump and food web dynamics. So POC is a source of food for zooplanktons in higher trophic levels, influencing the food web dynamics. So carbon sequestration studies, so investigating the role of ocean in the sequestering carbon and mitigating the climate changes. Marine food web analysis, understanding the distribution of organic carbon to support the studies on the marine food webs and ecosystem dynamics. So now I'm going to close this. So you can able to view from this first two graphs here. So this first graph which represents the chlorophyll concentration, and the second graph represents the sea surface temperature. So in the first graph you can able to visualize in this set of months here where there is a chlorophyll concentration is very high comparatively in sea surface temperature graph here. So during the low temperature time the chlorophyll concentration was very high compared to the high temperature. This is a sea surface temperature graph. So during the high temperature time the chlorophyll concentration has been reduced. So you can able to visualize from this graph like similarly in this setup here there is a high chlorophyll concentration is observed, and in this here you can able to in very low temperature there is a very high concentration of chlorophyll, and high temperature area during high temperature it has a very low chlorophyll concentrations. So in last we're going to calculate and print the area of chlorophyll-a and phytoplanktons and particle organic carbon. So for that we defined a function called calculate area image. We set a threshold and band name. So we defined a variable mask equals to image dot update mask update dot greater than threshold. So we are defining a threshold of around 0.1 for chlorophyll threshold and phytoplankton threshold of 0.1 and PO particle organic carbon of threshold of 0.1. So you can also change the threshold according to your choice. Just to calculate the area, I have defined this set of thresholds. So we define the dot greater than threshold referring to this values here, and we defined a variable area image equals to mask dot multiply doubly dot image dot pixel function dot divide 1 is to 10 power 6 to represent to convert to a square kilometers. We use this particular one, and variable area equals to area image dot reduce region reducer referring doubly dot reduce sum geometry referring to the study area. Spatial resolution is around 5000. This is the maximum pixel value, and we're going to print as area as band name plus area square kilometer and area dot get band name. So we have set this threshold for the area calculation. For chlorophyll we set around 0.1. So for the phytoplanktons we set around 0.1. For particle organic carbon we have set a threshold of 0.1. So now to visualize the area for this chlorophyll concentration and phytoplankton and particle organic carbon, we define calculate area chlorophyll threshold, output the layer as chloro-A, and calculate area for phytoplankton. We similarly done that. So to visualize the area for area covered for chlorophyll, phytoplanktons and particle organic carbon is given here, the area in square kilometers for the specific study area in California. It is in Gulf of California. So now here you can able to visualize it. So these are the different layers starting from a study area: chlorophyll, phytoplanktons, particle organic carbon, and SST stack, that is sea surface temperature stacked image. So this is a chlorophyll-A and this is phytoplanktons, and followed by we have particle organic carbon. So you can able to visualize the particle organic carbon, and last we have our sea surface temperature. So white areas which indicates high temperature, and the darker area which indicates the lower temperature. So you can able to see that. So in this video I have shown you the spatial and temporal analysis of water chlorophyll concentration using MODIS data in Google Earth Engine in Gulf of California as a case study. So thanks for watching, and please subscribe to our channel and give us a like. So the code link is given in the description. Thanks for watching.